Hello everyone, today we will be doing some series questions and finding out whether the series converges or diverges. So for our first questions, we have a unique one. Say we have a series of from 1 over to infinity of pi minus n plus n minus pi. Now, what can we do with this? Well, I don't think we can do the divergence test. So, what we are going to do is we're gonna start by separating it into two series. We can do this, but we can do this by pi minus n. Now, we are not entirely sure if doing this is actually the right way to do, but we will find out soon. So this is pretty much the same as from series S1 over pi to the n. Now, what can we do with this? We can use the geometric series test. This is the same as 1 over pi to the n. And from here, we can conclude that this series converges by geometric series because, as we can see, this is r. R equal 1 over pi, which is less than 1, so it converges right there. Now this is the first one. For the second series, this one, we can divide it again. Series of 1 minus pi, which is essentially the same as 1 over n to the pi. Now, there are many ways to do this, but the simple one we can do is to use the p-series test. According to the p-series, if p is bigger than 1, it converges, and if p equal or smaller than 1, it diverges. So let's find out. So 1 over n. So essentially we don't need to do any further steps. So we can just say uh, this series converges because by p series test, because p, which is now, well, 1 is because p equal pi, and pi is bigger than 1, so it converges. Simple enough. And because this is converges and this is converges, we can conclude the series converges because they both converge. Simple enough, but takes a while. So we can do the second questions we have today, and it will and quite a simple one actually. And it's the series from n to 2 to infinity of n ln n. So how can we do this? The simple way would be to use the divergence test. Maybe we can get away with using the integral test, but today we will be doing the divergence test. So to start, we can take the limit of the series and to the infinity of n over L and n. Notice that this is actually in the form of infinity over infinity once we plug in the n with infinity. So what we are going to do is to use the Hospital's rule. So again, write the limit. We take the derivatives of n, which is 1, and ln n, which is 1 over n. And we can conclude that this is the limit of n goes to infinity n, which is infinity. And since infinity is not equal to 0, the series diverges. By divergence test. Simple enough. So let's do our third question. For the third question, we will have series from n equal 1 to infinity n plus 4 over 3 and minus 6. Again, there are many ways to do this, but the first thing we should try to check is to try to use the divergence test. To do it, we take the limit again of the equation from which is n plus 1 over 3 and minus 6. Now this is also in the form of infinity over infinity, but a simple way to do it is to use the rational function limit theorem and just take the number of the highest power, which is essentially 1, and the lower one is 3, and that's our limit. And 1 over 3 is not equal to 0, so again, this is divergence. And according to the divergence test, if the limit is not 0, it diverges. By the divergence test. Simple enough. So the next thing we will be doing is, let's say we have a different questions. Now this will be an interesting one. So as n from 2 to infinity of 1 over n squared ln n. So if we take the limit of the series from, if we try to use the divergence test, we take the limit of n to the infinity of 1 n squared and n, we can see that this goes to 0. So divergence test does not work for this question. So we should try another thing. How about if we use, say, direct comparison? Now with the direct comparison, we can say that 1 over n squared ln n is smaller than, well, we are going to assume, well, first we are assuming that uh, series converges. So we try to find a bigger function and then we try to find whether it converges and matches. So say we need to find a bigger equation, a bigger fraction. So say we can use 1 over n squared. Simple enough. By removing the ln n, we essentially make, because ln n is on the denominator, we essentially make the fraction bigger in this. And then we can confirm our choices by doing 1 over n squared, which is converges by p series as p equal to, which is bigger than 1. Now we can say that because this converges and this is and or this is bigger than 1 over n squared, we can say that this is also converges by direct comparison. Alright, let's do another one of these for our last questions. We can do from n equal 1 to infinity of root n plus 3 over n squared plus 1. Again, we can try to use the divergence test, limit of infinity of this, and you can notice that n radical n is actually n to the 1 over n squared, and because the top power is less than the lower power, this will be 0 and divergence test will not work. So we can try to do the comparison test again. To compare, we can say that this is actually bigger than 3 over n squared plus n squared, right? Because we make the lower smaller, so this fraction is larger, and we can make it even larger by multiplying it by 4 of our radical n over n squared, and this is essentially the same as 4 1 over root n. Now we can find out from this infinity of n equal 1 over 1 over root. Well, I mean, this is not the root n. Oh man. Okay, so this is wrong. We can take that away. So we can find out whether this is converges or diverges. If this is diverges, then we gotta start over. Now we can see that this, we can notice that this is in the P series form. So this is converges by P series because P, well, this is multiply, equals 3 over 2, which is bigger than 1. Simple enough. Now because the 4 root n over n squared is bigger than this and bigger than that, our original equation, we can safely conclude that this converges by direct comparison. Oh, simple enough, but sometimes it can take a while to do.